Okay, I think you heard me before anyway, but I have to repeat the whole thing. I will not, because otherwise I will stay here for the whole seminar. I can give the seminar myself if you want. But anyway, it's great to have Bryan Weber here. And as I said, he was one of the fathers of this Monte Carlo event generator called Herwig, which is widely used by many phenomenologists and many experimentalists for many, many years. That was a huge contribution. I know him more from my time when I was postdoc in his group. I was there for 3 years, and he was also a leader in calculations of different resummations which are important for QCD observables. I remember now some Renormallon calculations and power-like contributions to perturbative observables, which were very interesting at the time. And more lately, he's been working on the matching of next to in-order hard matrix elements with Parton's hours in order to get a very good global description of observables, which are important in particular at LHC. And he's been also working on black hole production. I remember that also for a few years. He also wrote a code, which is probably the code to do simulations on black hole production at Hadron Collider. So his contributions are very broad and for many years, and crucial for phenomenology. So without saying much more, I would like to welcome you and to go for the seminar. Thanks.
Thank you very much. Thank you for the kind invitation and also the kind introduction. So today I will try to tell you something about simulating events at the Large Hadron Collider. I'll try to emphasize the ingredients that go into these programs and the theoretical status of these ingredients. I won't give many technical details, but just try to give the general outline and some comparisons with LHC data. But I have more technical details which we could discuss afterwards if necessary. So let's see if this works okay. Yes. So I'll just, for the people here who are not particle physicists, I will give some introduction very quickly on the standard model. And then I'll start by talking about lepton-hadron collisions, because that's a rather cleaner way of looking at some of the issues that arise in these collisions and what we have to do to simulate them, and then talk about hadron-hadron collisions like the ones at the LHC. I'll talk about some developments that I've been involved in that Agustin mentioned to try and improve the precision of these event generators, which has really become necessary in the light of the LHC data.
It's me, then. It's me. I interfere with the microphone.
Maybe we need less gain, I don't know here. Then, of course, I have to say something about the Higgs boson. So, again, the issues that arise in the simulation of the Higgs signal and the backgrounds. And a few brief words about beyond the standard model, for which, of course, we're looking very actively, and then some conclusions. So, the standard model consists of these particles here. We have the leptons, 6 leptons, 3 generations with the charged and neutral leptons, and then similarly we have 3 generations of quarks with the up and down type quarks from each generation. And then we have the bosons down here, the vector bosons, which mediate the interactions between these objects. And then we have, or at least now we've discovered that we have a scalar boson down here, which is the Higgs boson. So these are what you could call the matter particles. These are all fermions. And then we have the gauge bosons, the spin-1 bosons, which mediate the interactions. And then we have the scalar boson here, which gives mass to the other objects in the standard model. And the blue lines here summarize who interacts with whom, so that we have some sort of distinction here between the electroweak sector, which includes everything except the gluons, which are the mediators of the strong interaction, the QCD interaction, and the symmetries of these interactions are the exact SU3 gauge theory of QCD, and then the broken electroweak symmetry SU2 cross U1 mediated by the 3 gauge bosons of the electroweak interaction. So let's bear in mind that the Higgs boson down here doesn't interact with massless objects. So there's no line going from the Higgs boson to the gluon or the photon, which are the gauge bosons that remain massless after symmetry breaking. So let's first look at lepton-hadron collisions to see what kind of thing happens when you hit a hadron. When you hit a hadron with an electron, then you can have an electroweak interaction, which is then mediated by the exchange of some electroweak gauge boson, say a photon here, and then you can knock out one of the quarks, one of the charged objects in the proton, and the electron and the quark move off in different directions. And in fact, from the direction of scattering and the energy loss of the electron, you can measure the hardness of the interaction, that is to say the amount of momentum transfer that you have. And you can also measure the momentum of the struck quark that you actually hit in this interaction. And if you have a bigger momentum transfer, then you may hit some quantum fluctuation in the proton, which could be, for example, quark-antiquark pair here, which then you could find yourself with an antiquark being knocked out because the hardness of the interaction allows you to probe deeper into the proton to a smaller scale, and then you see these fluctuations. So actually, the first important component, perhaps, of the simulations that we're going to have to do is the momentum distribution of the various constituents of the proton. And then we have to remember that in addition to these so-called valence partons, valence quarks here, the up and the down quarks, this is the fraction of momentum carried, the distribution of the momentum fraction, called the parton distribution function. We have some of these so-called C quarks, that is quark-antiquark pairs which due to quantum fluctuations, and of course we have the gluons which bind them together by the QCD interaction, which are not themselves charged, so we don't see them directly, but we can infer their momentum distribution by subtraction from the total proton momentum of all these other components. And then we have to remember, as I've said, that what you see in the proton is dependent on the momentum transfer, so that as you hit the proton harder and harder, you find that you get less and less valence contribution and more of these fluctuations, particularly the glue and the C contribution increase as Q squared, as the momentum transfer increases, so that will have to be built into the simulation as well. So deep inelastic scattering, as I said, of an electron looks like this, and it knocks out a quark from the proton, but of course we have to remember that the quark is charged with respect to the QCD strong interaction, and therefore when it's knocked out of the proton, it doesn't just come out in isolation. It emits some radiation, some QCD radiation. That means some gluons. It also, of course, being charged, emits some QED photon radiation, and in fact the radiation patterns are more or less the same in QCD and QED, namely that the radiation goes mainly along the original direction of motion of the quark and the direction of the struck quark. And that means in diagrammatic terms that when you knock out a quark, then you get a burst of radiation along the beam direction in the same direction as the remnants of the proton remaining after the interaction, but actually coming from the hard scattering here. And then you also get some radiation coming out along the direction of the struck quark. So we can see right away that we will get some kind of hadronic energy along the beam axis and along the axis defined by the momentum transfer, which gives rise to what we call jets in the final state. Now, QCD being a very complicated interaction, a non-abelian theory actually has a coupling which grows very strong in the long distance region, and so what actually happens is that we don't see these gluons and quarks coming out individually. We see them confined in some way into hadrons in the final state, and so the things that are actually detected in the experiment are hadrons formed out of these quarks and gluons. But nevertheless, the important point which we will have to build into the simulation is that this confinement process is a local process in phase space, and that means that the energy flow and the quantum number flow, as far as possible, follows the gluon and quark energy and quantum number flow, so that these jets do emerge with the same kind of direction and energy as in the earlier phase of the interaction, where the final state consisted of quarks and gluons. So all this was found out, well, over many, many years, starting in fact in the 1960s in Stanford, but the last and best electron-proton collider was HERA at DAISY. That closed down in 2007, and I just wanted to show you an event there. So the detector for which I'll show you the event is the Zeus detector at HERA, and this actually looks superficially similar to what we have at the LHC, only much smaller. And in that case you had protons coming in one side, electrons coming in the other side, and then a kind of concentric cylindrical set of detectors here which detect the outgoing particles. And if you open out the cylinder here, this is a view from the side, a view from the end looking down the beam direction. If you open up the cylinder to a plane here, then you see this Lego plot here of the energy deposited in various regions of the detector, and you can see very nicely the electrons scattered here and the quark jet coming out as I showed diagrammatically earlier. And you see this is quite a nice clean event. In this case, electron-proton is a fairly clean process. There is, of course, also a beam jet, remember, but the detector has a hole necessarily where the beam is, so actually you don't see the beam jet in this display here. So what's the theoretical status of this description? Because this will be important for the simulation. Now, the hard scattering here is a process which you can calculate to, in principle, to arbitrary orders in perturbation theory. So that's a very well-defined calculation within the standard model. So we can do that to exact fixed order perturbation theory to any order that we have the computing power for. Now, this gluon radiation also in principle is a well-defined perturbative process, but it's already of such a high order. Typically we want to study final states in which there may be dozens of quarks and gluons in the final state before we have to tackle the confinement problem. And so in practice this is too difficult to do in fixed order perturbation theory, and in any case we don't have a fixed number of quarks and gluons. We have fluctuations from event to event in the numbers here. So what one actually does is an approximate all orders treatment that I will explain a little bit more, but basically one picks out the terms in perturbation theory which are most enhanced order by order and tries to treat them to all orders in some fairly well-defined approximation scheme. And then finally we have confinement, which in this context, in the dynamical context of converting this final state of gluons into hadrons, is unfortunately not treatable by any of the non-perturbative methods that we have at our disposal, which are mainly lattice simulations, so that we have to model it with a model for confinement and hadron formation, which is purely empirical and has parameters and has to be just fitted to the data. But the crucial thing about this is that it's a a local model, as I already said, so the mechanism has to preserve the flow of energy and quantum numbers in the final state, and that gives us some clue about what kind of model we should have. So let's go now to hadron-hadron collisions, where of course we had two big hadron-hadron colliders, the Tevatron at Fermilab, which is now closed, but nevertheless gave us a huge amount of data, some of which I will show, which very much constrained the modeling of hadron-hadron collisions. It was a proton-antiproton collider, so in that respect there are some important differences from the LHC, which is a proton-proton collider. Of course, the energy was also lower. But the Large Hadron Collider, as I said, is proton-proton, and it's run up to now at 2 energies which are both below the ultimate design energy of 14 TeV, roughly half the final energy, and it will actually, when it starts up again, shut down at the moment to be reconfigured for higher energy running at the end of 2014. Then we will have a range of energies from 7 to 14 TeV. So the two main experiments are on opposite sides of the ring at the LHC. The ones I will speak about are the general purpose detectors ATLAS and CMS. There's also LHCb for doing flavor physics primarily with B quarks, and there's ALICE for heavy ion collisions, because the LHC can in fact also accelerate and collide heavy ions. So ATLAS looks like this, superficially like the Zeus detector, except on a much, much bigger scale. Here's a human down here. I'm sure everybody's seen this kind of picture. It will be important for us, though, to know what kind of particles we're primarily looking for here, which are hadrons, of course, which are caught in a calorimeter. Well, the charged hadrons leave tracks in the inner detector here, and then they deposit energy in the calorimeters here. And then there are muons which escape from the calorimeters and are tracked and bent in this outer muon detector arrangement here, which actually is responsible for the name of the detector, because it has gigantic toroidal magnets, as you can see here, to give you a magnetic field which runs around the circumference. And inside is the central detector. And then here's an event display where you can see the muon detectors, because this is in fact a Higgs candidate decaying to E plus E minus, mu plus mu minus, where you can see the two muons depicted coming out here, and the muon detectors which are triggered by their tracks, and then you can see the electrons depositing energy in the electromagnetic part of the calorimeter, and then you reconstruct the mass of these objects, and you find it's consistent with the Higgs mass. The other big experiment, CMS, again, to a theorist looks superficially similar. As the name implies, it's much more compact than ATLAS. It's very, very dense. Everything is therefore a little bit smaller in the overall size, but it's a very massive device. And here's an event display from CMS, which again is an E plus E minus, mu plus mu minus, an early candidate for Higgs decay. Oh, I should have pointed out, remember I said in the electron-proton collisions at Hera, things were relatively clean, and you can see right away in these LHC events that things are not so clean. There's a lot more activity going on. We haven't just produced a Higgs boson here. We've produced a whole lot of hadrons in the final state, and so that's one of the challenges of simulating these events, that we have much more activity going on in hadron-hadron collisions than we had in EP. So what actually happens? Well, let's take a very simple example. We have proton-proton here with a gluon exchange, and then of course now that can knock out one quark from each proton. So we have the beams, or the remnants of the beams, continue in their original direction, but we have two objects going out, and these two objects form jets. And then there's the further complication that I alluded to earlier. The extra hadronic activity is going on, at least partly, because there are extra quarks, extra constituents in the two protons which can interact with each other at the same time, so that you have multiple interactions. These are two protons with two dijet productions. So actually we would see four jets here. Although in general, it's very unlikely that we will have two very hard collisions with big momentum transfers which give very energetic jets. So we have a relatively high probability of extra jets with rather low energy, and there may be more than two in that case, that we may have a lot of extra what we would call soft secondary or extra collisions going on. And this, I should emphasize, is a collision between two protons, not two bunches of protons. Of course, we also have, in each bunch from the accelerator, we have many protons. So there will also, in general, be many different proton-proton interactions in the same beam crossing. That's something called pile-up, which in principle can be distinguished from this multiple interaction in a single collision, because the vertices from which the tracks radiate will be slightly different for collisions involving different protons. And so, in principle at least, we can identify the difference between multiple interactions and pile-up interactions. But nevertheless, pile-up becomes a big problem for the experimenters, because they have to perform this sorting out of the interactions, and they have much more stuff in the detector than they would otherwise. So we have the basic similar components to the EP interaction, but in addition we have this multiple interaction which gives rise to what's sometimes called the underlying event, the extra activity that we saw, which takes place in conjunction with any hard scattering process, and it involves the other quarks in the colliding protons, the other constituents in general. And then we have gluon radiation from all these objects. So we have beam jets going out in both directions, and some general activity associated with these multiple interactions. And then we have, when we have dijet production, we have the two jets from the struck quarks, struck constituents in general, and these are confined, and then hadrons are formed or hadronized to give rise to the jets of hadrons. So all this has to be simulated if we want an accurate representation of this. And of course, for any non-standard model process that we might be looking for, then it will inevitably involve acceleration of the constituents of the protons, even if it's due to creation of some new object. We will still get lots of QCD radiation, so we still have the challenge of simulating all this stuff, even if the process we're interested in is not a standard model process. So here's in fact a dijet event where you can see very nicely in the Atlas experiment, this is a dijet in which the invariant mass of the combined two jets is 4 TeV, so this was a 7 TeV collision in which 4 TeV went into the invariant mass of these two jets. Very, very energetic. And now jets up to this energy and above have been regularly produced. You can see there's some other jet activity, as I said, probably due to this multiple interaction going on in the same event. Now, an important theoretical point about this, which allows us to do calculations, is the so-called Qcd Factorization Property, which says that the cross-section for any kind of interaction can be written in the following form as a convolution of the distributions of the partons in the two protons, these functions f here, distribution of parton of type I with one of type J, And these two partons collide to make this final state X. And the energy of the collision is related to the beam energy by these energy fractions, x1 and x2. And then, of course, remember that there's a scale involved. As I pointed out, the parton distributions depend on the scale of the momentum transfer at which they're measured. And so in this whole expression here, of course, that scale ultimately has to cancel out, because the cross-section can only be a function of the beam energy if it's integrated over all other kinematic variables. And so there has to be a cancellation between a scale dependence in the hard process cross-section and that in the parton distributions. And that is the factorization theorem that says that order by order, that is the case, that the scale dependence of this calculated hard process cross-section will always cancel order by order in perturbation theory with that of the parton distribution. So that allows us to do this simulation. Usually we will choose a scale here which is characteristic of the hard process. For example, if you're making top quarks, then the top mass. If you're making the Higgs boson, then the Higgs mass. And then convolute it with these functions at the same scale. But if we want to improve the calculation and calculate an extra order, then we will find that order by order that arbitrary choice cancels out in the final result. Here is the dijet mass distribution. Actually, this is an early plot, but it hasn't, as far as I know, been presented much more accurately since. And you see that the agreement up to this scale, which I showed you, of 4 TeV or beyond with the standard model is extremely good. This is just a technical point for those of you who are not particle physicists. This is the integrated luminosity. This summarizes the amount of data that went into the plot. It says that you would have 5.8 events if the cross-section measured is 1 femtobarn, that is 10 to the minus 15 barns, where the barn is a typical size of a moderately large nucleus. So you can see that we're already probing the very, very small scale structure of the proton in this interaction and not seeing any sign of deviations that might be associated, for example, with quark substructure. If the quark is not an elementary particle, then one would expect some deviation from this hard scattering distribution. And as I said, this of course is deduced from hadron distribution in the final state. So it's compared with a primary process which is just quark-quark or parton-parton scattering. Out here it's mostly quark-quark scattering. And then we use the factorization theorem to enable us to make a prediction, an accurate perturbative prediction. So what about event generation? How do we put all these theoretical aspects into a program? What's the point of this exercise anyway? Perhaps I should say what we're aiming to do with such a program. We want to produce simulated events. That means files of in principle track data, simulated track data, lists of particle identities and momenta of objects that would actually be observed in a detector, which as far as possible reproduce those of real collisions. And we will simulate the quantum effects, the fluctuations from quantum mechanics with pseudo-random numbers in the computer. And the purpose of this has been, well, in the past it was very important for designing the ways to carry out experiments and analyze their data by using simulated data and putting it through various analyses to decide how to discover, for example, the Higgs. Once the experiment's running, this kind of simulation is also essential for working out the corrections due to the characteristics of the detector. For example, the responses of the calorimeters are very non-linear and depend on the substructure of jets, and these have to be simulated and corrected for. Similarly, you have to impose cuts on the data to try to isolate a signal. You have to know how these affect your measurement, and this has to be done with simulated data for which you know the quote truth. And then, of course, you want to compare with the standard model and measure its parameters, and also you want to estimate new signals by putting new models into these generators and seeing what they would, what consequences they would have at the level at which you can actually measure. So once again, you see the different components. Now, so the gluon production, or the radiation, which I've said always emerges when you scatter these constituents, is represented in what we call a parton shower approximation. So it's like an electromagnetic shower, except it consists of quarks and gluons instead of photons and electrons. And then we have to simulate the confinement process and the so-called hadronization, that is the actual formation of the hadrons that come out into the detector. And then, of course, the decays of the unstable hadrons, which is actually a very important component of the process, because many of the primary hadrons are unstable and decay by either strong or electroweak processes. So a little bit of technicality here. The parton shower approximation, as I already said, is a scheme where we try to keep the most singular, the enhanced parts of the QCD matrix elements, order by order, to all orders, and simulate them in this Monte Carlo approximation. And the two kinds of singularities that we can identify are collinear singularities, where a parton, that is a quark or a gluon, splits into two almost collinear partons. For example, a quark here emits a gluon at a small angle. Then there is a function called a splitting function, which tells you the energy fraction and the azimuthal distribution of the splitting. And then you have a singularity which you see is divergent as the angle of emission goes to zero. That is the collinear divergence. So this d psi over psi is the enhancement that you want to sum to all orders. And then there's another, in every order, another source of singularities, which is the so-called infrared or soft singularity, which comes from the fact that you have a massless gauge boson here, which means that whenever any of these gluons has a low energy, then you have d omega over omega, where omega is the gluon energy divergence, just as you do in quantum electrodynamics. You have an infrared divergence in the spectrum, which means that you get a large amount of soft gluon radiation. Now, it turns out that you can simulate these, or you can generate these singular terms to all orders by a rather simple Monte Carlo Markov process, where you basically radiate in an angular ordered sequence of emissions in which the angles of emission get smaller and smaller until you reach some cutoff, some relative transverse momentum beyond which you perturbation theory doesn't work, because the QCD coupling is growing all the time as you emit, where the long distance properties of the theory become divergent. So at a certain scale, at a certain transverse momentum here, you stop the process and have your hadronization model. Now, the kind of model that I've been involved with mostly, there are different models, although this is one of the popular ones, is a so-called cluster model, which is based on the property of perturbation theory, which is very nice in QCD, which is a so-called pre-confinement property. And it says that actually the final state organizes itself in such a way that there are local, in phase space, color singlet objects in the final state after this showering process has gone on for a certain time. In fact, if you cut it off at some scale, then you will find that the color structure of the final state is rather naturally formed into color singlet local objects called clusters. And I've tried to depict that here in a schematic way. Each gluon in the previous diagram in an approximation can be represented as a color-anticolor pair. That is actually in the approximation that there are an infinite number of colors, but it turns out to be quite a good approximation. And then you see if you follow each color line, you find an associated anticolor line which is nearby in phase space, and so you can see that you're going to be able to form colorless clusters here, which are these yellow things, which are then candidates to be simple proto-hadrons, color singlet, colorless objects, which can decay into hadrons in some simple phase space model. So that is the mechanism in the cluster hadronization model. And then you have some hadron formation in a simple model, which is phase space-like, and then these hadrons decay, and you have your final state. So I show here the basis of this assertion about color pre-confinement. If you take this parton-Shower approximation, and you take processes with different hard scattering scales here, this is in fact electron-positron annihilation, but the same is true in any process, and you vary the scale of the hard scattering, the cluster mass scale, at a certain transverse momentum scale at which you stop the parton showering is universal. And this is then the universal distribution of the cluster masses that you use in your hadronization model, and it peaks up at some rather low scale, so you can use a very simple model for decaying these clusters. So this, you see, is an approximation scheme which is based partly on exact perturbation theory, partly on approximate perturbation theory, partly on modeling. So it's, in principle, an imprecise tool which is very flexible, like a Swiss Army knife, but perhaps tries to do too many jobs at once, and then suffers for not being sufficiently precise. So what we've been trying to do over the past 10 years in the light of the data is to make these tools more precise, and that's what I will speak about for the rest of the talk. I should say there are three event generators which are in heavy use at the LHC. The Herwig that Agustin mentioned, that I've been involved with. And then there's Pythia, which is actually the oldest and but still the best established of these generators, which uses a different hadronization model. And the showering looks very different, but is actually fairly equivalent. And then there's a newer program called Sherpa by Frank Krauss and collaborators, which is a combination of the ingredients in these two with its own variations. And there's a big review article written by about 16 of us on these programs, which gives more details. So what are the problems with these programs? Here I show some plots of data and simulation compared. This is actually for the process of vector boson production in conjunction with any number of additional jets. And you can see the strengths and weaknesses of these programs. This is actually Herwig and Pythia are compared here with the data from the Tevatron, first of all. This is a D0 experiment at the Tevatron, and then Atlas data over here from the LHC. And you see, this is the transverse momentum distribution of the vector boson itself, and the agreement is very good in shape, but when you look down here, where you take the ratio between the data and the simulation is systematically low. There's always a discrepancy in normalization that comes about from the fact that the event generator is using only a leading order perturbative treatment of the hard scattering process here, and that leads to a bias, a systematic difference in normalization. And the next problem you see is that if you demand additional jets in the final state, which come from extra gluon, extra parton emission, then also the shape begins to deviate, and you have systematically too few high transverse momentum jets in the final state. And this is the first jet, and this is the second jet. That is the jet with the second highest energy compared with this one. And you see here both the normalization and the shape are becoming too low. So what we need to improve in the program, assuming that there's no real violation of the standard model here, is we need to treat the precision of the hard scattering to next to leading order, at least in perturbation theory, and we need to simulate better the production of additional jets in the final state. And that's where all the work has gone in. Now, this is not an entirely trivial thing to do, because you have the problem of double counting. Suppose we have a hard process like this one, which is actually a bit more complicated. Its quark-quark goes to quark-quark Z0. And we want to do a next to leading order calculation. Now, the next to leading order calculation of this hard scattering involves two kinds of corrections. There are loop corrections, where you have a virtual gluon here, and then there are real emission corrections, which are the same order when you square the amplitude, that where you have an extra parton emitted. But of course, our parton shower approximation already did, in some approximate way, all orders of perturbation theory as far as the real emission, and incidentally also the virtual loop contributions are all treated in an approximate scheme. So what we have to do is ensure that there's no double counting. In other words, we have to avoid counting twice this extra emission here, and make sure that we have the accurate next to leading order. Similarly, if we want to simulate multi-jet final states here with two extra jets, then of course we can't just use the lowest order matrix element for this extra jet production, because we will have double counting when we add the parton showering. So there have been several schemes evolved over the past 10 years or so. First of all, this next to leading order matrix element calculation without double counting now exists in two forms, slightly different forms. One called MC at NLO, which was developed by Stefano Friccione and myself, and then so-called POWHEG, which is Paolo Nazon and collaborators, is an alternative implementation. And then the other problem of multi-jet production, the matching with next to leading order is, as I said, a problem. One problem of double counting. The other is the counting of multi-jet final states is a problem of merging with leading order multi-jets, and that has three basically very similar implementations now, starting with the one that Stefano Catani and Frank Krauss and his student and I developed in 2001. That's called CKKW. And then the dipole Lomblab scheme, which is almost simultaneous, and Michelangelo Mangano's scheme a little later. So let's first talk about matching to next to leading order. This MC at NLO scheme has a very simple basis. You simply take the parton shower approximation and compute exactly at next to leading order what it contributes, and then you subtract that from your next to leading order calculation. So this depends on how you do the parton shower, so it's dependent on the event generator that you're using for the parton shower. The great advantage of this scheme is that a technical point which is actually very useful is that this procedure cancels the soft and collinear divergences of the exact next to leading order calculation, because the Monte Carlo already treats those regions accurately. And so you end up with a more stable numerical scheme even for doing next to leading order. However, this subtraction, because it involves negative contribution, can end up giving a so-called negative weight, which means that your hard scattering probability might be negative. Then it represents a correction to your distributions, which you have to subtract. The experimenters initially didn't like that very much, but I think they got used to it now. Powheg was a positive weight hardest emission generator, which was a way of avoiding this negative weight defect, which says that instead of subtracting what the parton shower does, you generate the hardest emission using the exact matrix element instead of the parton shower. And so then you have to do a certain amount of juggling to make sure that they fit together smoothly. But that does have the advantage of greatly reducing this problem of negative weights. Yes?
Before you continue, is there any problem with double counting with respect to the structure functions, I mean the parton distribution functions, or because you are not talking about that, but I guess there is also an issue in there at which level of perturbation can you
Yes.
not do double count?
Yes. Well, that's implicitly taken care of in these schemes, because you do, I mean, the evolution of the structure functions is associated with the collinear singularities along the beam direction. So when you do the subtraction to take those out, you actually take out that part of the evolution of the structure function. So yes, the two sides, yeah. So yeah, that's part of the that's probably the technically most difficult part of the correction. But then you end up with the Qcd factorization, as I mentioned. So what happens is, as you can see, you cure this problem with the normalization, or at least you greatly improve the normalization. Here's now the same Z0 production data for Herwig++ and Herwig++ with the Powheg next to leading order matching prescription in dashed and solid lines respectively. And you can see in the ratio plot here that you've actually, I should have mentioned that the yellow region represents the errors on the experimental data. So you can see that you've come within the range of the data. Similarly, gamma-gamma production, this is of course an important background for Higgs, for the Higgs search, and you get the leading order is too low, Powheg agrees with the rate and the distribution. So many plots I could show you. Here's the W asymmetry, that is the difference between W plus and W minus longitudinal distributions at the LHC, which is very sensitive to the parton distributions. And here you see the simple leading order Monte Carlo gets both the shape and the normalization wrong, whereas the next leading order correction is excellent. This is the same distribution over a much wider range of longitudinal rapidity here, which is essentially the longitudinal distribution of the vector boson. And you can see that you have, this is actually MC at NLO and this is Powheg, so both of them do very well. Here's the top court production in MC at NLO at the in the Atlas experiment, where many distributions compare excellently with the top court production. Now the multi-jet problem, I won't dwell too long on this because I'm running short of time, but then we have a rather different problem, which is how to generate many additional jets in leading order without double counting when you superimpose the parton shower. And the method that's been adopted here is to divide the phase space into regions inside, essentially inside the jets, and those regions between jets, or the distribution of the jets themselves, are separated according to some cutoff, which is called Q cut here, which is essentially the relative transverse momentum of the particles relative to the axis of the jet. And you generate, with the parton-shower approximation, the distribution inside the jets, and you generate the distributions of the jets themselves with the leading order matrix element. And then there are theoretical procedures to cancel the leading behavior on this arbitrary separation parameter. So that's the trick in that case. And you can see that here is the W plus jets at the LHC from CMS and Atlas. And in both cases, the simple parton-shower approximation is systematically falling below the data as the number of jets increases, as we already saw. That is shown by the green here and by the little crosses in the Atlas. And when you do this merging procedure, you find that you get very good agreement with the additional number of jets, even up to 4 extra jets. And this. Yeah, of course, that's a parameter which is not shown here, but it's something that you have to. I mean, you can look at it. Obviously, you make different choices and show that you get stability. So I would guess that probably the Q cut here is somewhat below the jet transverse energy cut of 30. It's probably about 20, but I'm sorry the experimenters haven't shown it here. But in principle, it should be some number somewhat lower than your jet transverse energy cut.
So you look for stability. In order to fix it, you look for stability then?
Yes. Yeah. As I say, the theoretical procedure is to cancel the leading behavior, so you have to check that that's actually true. So here's W plus jets. These are actually all the vector boson type cross-sections at the LHC from CMS and Atlas, up to date from the runs in 2011-2012, and there's no sign of any deviation from the standard model predictions so far in any of these channels. I should have said that the vector boson plus multi-jets is an important channel for new physics searches, because many new physics processes give you jets plus leptons plus missing energy, which is what you see in W plus jets. There are some discrepancies which, if you were very optimistic, you could say were due to new physics, but possibly are due to defects of the simulations. For example, in the flavor of dijets, I showed you the transverse momentum distribution of dijets, but if you look at the decomposition in terms of the jet flavors, that is the quark species that are contributing to the jets, you find that in B jets you have many more high PT B quark jets than the models predict. So I would suspect that that's a defect of the flavor treatment in the parton-shower approximation, which is quite tricky for heavy quarks. But there is this discrepancy with the.
In fact, maybe this Q cut that she was commenting has to do with that, isn't it? I mean, the fact that you have to adapt the Q cut differently for the different flavors.
Yes, although this is just dijet production, so it's not very sensitive to this multi-jet merging. This is Powheg, so this is just next to leading order. Yeah, dijets.
I mean, the question, saying in different words, is how do you define the error of your estimation here in terms of which parameters?
Yes, these are just statistical errors shown on the Monte Carlo, I suspect. And it's true, I think the theoretical errors on the Monte Carlo are much bigger. It's very tricky to. The technical problem is that you can have, say, a gluon which fragments into a B and a B bar. And that is a process which you have to treat quite accurately in order to get the right number of B jets in the final state. So I suspect that gluon to BB bar is badly modeled in these programs, and that there's more high momentum B quarks from that process. That was always very difficult to get right at LEP, and this is way beyond the energy range of LEP. This is at 300 GeV jets. Okay, so let me spend a few minutes on the Higgs boson. So the Higgs boson looks like this because this is the representation of the Higgs boson at the Paralympic Games last year in London. I was puzzled to see that everybody thinks the Higgs boson looks like this, and then I found that the BBC gave a program earlier before the discovery in which the Higgs was represented by this blob here, which is a shiny thing with sharp corners. So that's what the Higgs boson has become known as, at least in the British imagination. So, but as far as we know, it's a scalar, so I don't think it has any interesting structure like that. And the funny thing about the Higgs, of course, as I pointed out already, is it doesn't interact with the photon or the gluon, whereas the discovery of the Higgs was actually in gluon. Gluon goes to gamma gamma. So how did that come about? And I have a little animation here that lets remind ourselves that when you have this gluon exchange between two protons, you can have one of these quantum fluctuations where you have actually a heavy quark pair produced. And of course the top quark interacts very strongly with the Higgs because Higgs basically interacts in proportion to mass, and so that can very easily fluctuate in turn into Higgs, and then the Higgs can fluctuate, for example, back into a top quark pair and make a photon pair, so that you have production through TT bar through this triangle diagram, which although it's high order has a very strong coupling at this point, so that it turns out to be the dominant mechanism for Higgs production. And then you can have the same mechanism for the decay, because the top quark is of course also charged, and therefore it couples, unlike the Higgs, it couples to the photon. Or indeed you can have a W boson loop, because the Higgs interacts strongly with the W, and the W is also charged even more than the top, so you can have this process here. And therefore you have gamma gamma goes to photon photon through a Higgs, even though there's no direct interaction. There's another production mechanism which is closely related to that decay, which I already showed, is you can have, of course, the exchange of W bosons. This is going to be a weaker process than the gluon exchange, but on the other hand you have a direct coupling to the Higgs, so this is a competitive mode. And then of course you get dijet production, and the jets associated with this process go mainly forwards, and then because you've got W bosons here, you don't get the additional gluon radiation that you would in a gluon exchange process, so it's actually has a different kind of final state which you can simulate and use to detect this process. So here's the classic two-photon signal here. You see there's a lot of activity. This is probably a gluon-gluon fusion because it has a lot of hadronic activity in the final state in addition to the photons. But the photon is such a clean signature that you can pick it out. And these are the discovery plots, which I expect everybody's seen from the original papers, which at that time gave overall something like 5 standard deviations of discovery, which allowed them to say that they had discovered a particle. Now I wanted to just draw attention to the theme of this talk, which is the event generators. Here are all the event generators that were used for the signal. This is gluon-gluon fusion, vector boson fusion. There are some other production processes in association with vector bosons and top quarks, and these were simulated with Pythia and Pauheg. And then all these background processes with a whole diversity of programs, each one being used to get the best possible precision for each background. So what was interesting early on was that when you did the calculation within the standard model, you found that in fact the numbers of events produced were somewhat in excess of the expectation in the gamma-gamma channel. And when you look at the original data, for the different production processes, you see Higgs to gamma gamma was always above the expectation. This is normalized to the standard model, so 1 means the standard model prediction. And both Atlas and CMS were seeing an excess, which caused a lot of theoretical activity, although it wasn't what you would call very statistically significant. And since then, it's interesting that the CMS experiment at the Morion meeting last month presented their more or less their full data sample from last year, which now is in excellent agreement with the standard model for all visible modes. And so that's the old data, this is the new, so you see the gamma gamma has gone down a bit. But nevertheless, if you combine all the channels, you've got many, many standard deviations of precision in the signal. And the Atlas update doesn't look very different from the old times. There's still some excess in gamma gamma. The error bars have come down a bit, but everything is still, I would say, in good agreement with the standard model. Of course, many, many other things to be confirmed. Some of them already showing indications that they are confirmed. For example, the spin and parity of the new particle is most consistent with 0+ as expected in the standard model. All the different production channels are more or less in agreement as far as we can see. The self-coupling of the Higgs is going to be very difficult to verify at the LHC, although it's an essential part of the standard model. The total width is very, very narrow for an object of this mass, and that will be very difficult to verify. The different decay modes with their percentages are all predicted, of course, and one can expect in the long term that the LHC will either confirm or otherwise these predictions to within the 10 to 20% precision, as shown in this schematic imagination of the final results from the LHC by Michael Peskin last year. Peskin used this plot to advertise the fact that if you have a linear collider, if you build a linear collider, as maybe the Japanese are proposing, then you can get down to 5% in most of these couplings of the Higgs boson. So that would be one of the main justifications for such a machine. So the status of the standard model is that, as far as we can see, it's a perfectly respectable renormalizable quantum field theory. All the predictions that it makes are computable in principle and have been verified within the experimental uncertainties. It's not a very beautiful theory because there are a number of instabilities and so on, but there's nothing fundamentally wrong with it. And here I show the consistency, which I think this is a rather beautiful plot here. This is the prediction of the W boson and top masses from the Higgs boson mass, taking into account the other standard model parameters, is given by this blue region here, and the experimental data on the W mass and the top mass fall within one standard deviation of this prediction. And here are all the other, well, not all, but many of the other predictions of the standard model and the deviations of the data from the best fit to the theory, where you see that they're all within 1 to 2 standard deviations and have just the expected kind of distribution if the theory were correct. So, of course, we'll keep looking for things beyond the standard model. I won't go into the arguments for beyond the standard model, but the LHC is looking at every conceivable, the experiments are looking at every conceivable distribution to try and find, for example, 7 jets with plus missing energy, a plot of a certain observable for these events here. There are 7 jet events, of which one is shown here, and but even these seem to conform to the standard model insofar as we can predict this process. There are endless plots of searches for different signals, shown here with the scale to which the exclusion of new physics has been driven. This is from, you see, just a week ago. The standard model the SUSY, the supersymmetry searches now extend in most channels up to 1 TeV. other kinds of exotica like black holes, extra dimensions, leptoquarks, quark substructure, all these things are excluded up to something of the order of a TeV. So the LHC will come on again at the end of 2014 at higher energy, and then we may well see new phenomena. Of course, there may be new phenomena lurking in the slight deviations from the standard model in the present data. They will keep analyzing, but so far the standard model reigns supreme, I would say, and apart from other physics like dark matter and neutrino masses, as far as the LHC is concerned, it's in very good shape. Plenty of scope for new discoveries, however. Thank you.
So, any questions? Let's try to use the micro because otherwise it's not very easy for everyone to listen.
You mentioned that they are very it's much more challenging to do the matching with next to in order. What are the main complications there?
Yeah, well, the MC at NLO method becomes extremely laborious because you have to compute two loops, just what the Monte Carlo is doing, which it may be more feasible with this Powheg method. And you have to generate the first and second most energetic emissions to two loops and match it onto the event generator. I think it will happen, but only in those cases where it's really essential, I guess. So I don't know, unless it's possible to automate it. But next to leading order is, even in perturbation theory, is very slow. Even when you may compute the amplitudes, but it's a different matter to actually generate the efficiency to generate the distribution. So.
I have another question. When you compare the two most famous generators, yours, Herwith, and PCR, which for me is fascinating because they are really different. One is based on the string-inspired thing, and yours is clusters, which is qualitatively different. And to me, it's really fascinating, the agreement between the two.
Yep.
But okay, going to the detail, how do you compare in error? How do you estimate the errors that you predict roughly? It's a very technical issue, but when you make a prediction in this kind of event generators, you have to provide a prediction with an error, which depends on the parameters of the two generators. How do you compare the two predictions? It's really, to me, the fact that they agree always was an issue which was fascinating because they are really qualitatively different.
Yeah. Yes.
When I have to explain that to the students, I really don't know how to do it. I teach particle physics at low level or standard.
Well, I think the agreement has to do with this local property of hadronization, as I mentioned, that although they use a string and we use clusters, their string is connected in such a way that it respects this local property of the hadronization. So our clusters sort of follow the shape of their string, and their string follows the distribution of our clusters. So it's not such a big difference as one might initially think. But of course, the question of estimation of errors of these programs is a big problem because they have parameters, as I said. So in principle, you could vary the parameters and see what difference it makes. But of course, the parameters, you know that when you vary the parameters, then certain other data sets you will no longer agree with. There's a vast body of LEP data and HERA data that has already been fitted with these parameters, and you know that if you vary them, you may get some variation in the LHC, which is acceptable but will not conform to the other data sets. So still, in principle, you can, of course, there are programs for varying these parameters and getting some idea of how far you can vary them and still remain reasonably consistent with all the data you put in. There's a thing called Professor, which is a special tool for this, which is you can read about in our review article in that physics report. And then, of course, the perturbative aspects you handle in the usual way, that you vary the scale and see what the scale dependence of the prediction is. With these next to leading order calculations, then you can certainly do that in the same way that you do in fixed order. In the matched generators, you can do the same thing. So scale variation, parton distributions, you can use different parton distributions, and you can vary the parameters. But yeah, it's a problem because the experimenters like it when Pythia and Herwig agree, and then they say there's no systematic error on the prediction. But of course, they agree because they've both been tuned to the data. Yeah.
So
Yes.
I was just going to ask whether there were no free parameters or there were free parameters, because
Yes.
the effect of matching the data is different if you have a parameter which you can change,
Yes.
or if it's just completely free parameters. So
Yes.
more or less
In the
answers.
cluster model, there are not so many parameters. I think it's fair to say that, and I think the Pythia people agree that there are not so many parameters in the cluster model. Because you're rather constrained, you can vary this cutoff scale on the parton shower, which varies the shape of that cluster mass distribution, but you can't vary it very much without getting into trouble with the divergence of the strong coupling, for example, which is around 200 MeV. The Qcd coupling in perturbation theory is divergent, so you can't vary the cutoff much. And then there are parameters for the decay of the clusters, which you can vary. But generally, the experimenters have about 5 parameters that they vary. And it's quite amazing, the huge data set that you can fit with 5 parameters. There must be some truth in it. It's so constrained.
But are the parameters tuned differently for different fits, or is it so when they provide, for instance,
Yeah. So.
do they fit independently the parameters for each of the plots, or
Oh no,
it's
no.
a joint?
No, I think most of the plots I showed you are just out of the box event generator. They haven't done very much parameter tuning at LHC yet. The big problem for the LHC experiments actually has been with this underlying event, which was not constrained by the LEP and HERA data. So the underlying event, that is the multiple parton interaction, is by far the least constrained. Well, it's constrained now by the LHC data, and it's very difficult to get agreement with the LHC data on the underlying event. That is the extra hadronic activity, not the jet distributions themselves, but what else is going on in the final state. Because the multiple interaction depends on the distribution of partons, not only in momentum, but in actual transverse space in the proton, you see. If the protons collide like this, then you have a few partons overlapping, and if they incline head-on, you have to know the profile of matter distribution and a flavor distribution in the proton, which is not constrained by other data. So that's something which is still a big underdevelopment. It's a kind of messy, theoretically messy, ugly problem, but it's important for the experiments. Yeah.
Okay. Any more questions? Well, if not, we thank Professor Weber again, and